Okay, statistical modeling. Statistical modeling. Again, we'll be looking at statistical modeling, and in case you're wondering, I think it's just of primary interest for you and for science. That's why I keep on telling that. Let me start with a little story again. Okay, so the story goes like this. Here, that's you. You work as a data scientist. Say it's your first job after graduation. Nice job, very well paid. Work as a data scientist, and your client of today. That's let's call him Don. So that's Don. Don is a very rich guy from NYC, and he's into property. He possesses a lot of houses in New York, and he's actually approaching you today with the following question. He would like to know, hey, Sebastian, what's actually the connection between the number of rooms my house has and the value I achieve when selling the property? Okay, so the number of bedrooms in connection with the money you get when selling it, and you crunch the numbers. So here we go, and then let's take here the regression line, which is nothing else, by the way, nothing else than a summary of the data, a summary of the bivariate distribution of bedrooms and the price you get when selling the property. So it's in essence descriptive statistics. What we do here, we summarize again this bivariate distribution, this joint distribution of those two variables in a line, using a line. Okay, so here's the analysis, and so you can tell Don, all right, Don, the more bedrooms your property has, the more money you're bound to get when you sell the house. For instance, say here that's around one bedroom, and here, I don't know, 5 bedrooms. The money you get selling here is on average much higher than you get when selling a house with, say, 1 bedroom in comparison. So Don is quite satisfied with this idea, and he keeps staring in the air, and then he says, oh, I've got an idea. I've got a beautiful idea. I built a number of walls in my houses, and say, Don tells you his house, or the property he's speaking about, has, say, 3 bedrooms, and he will just build a wall, he says, in each bedroom, so you'll come up with 6 bedrooms. And according to your model, the more bedrooms, the more money you will achieve on selling it, because it used to have 3 bedrooms, now it will have 6, so more money, and that's of course beautiful. So that's Don's idea. You, being a data scientist, you're of course a little bit skeptical with that idea, and probably you don't have to be a data scientist to be skeptical with that idea. Common sense may not really agree with the notion that the more rooms, the higher the money, in some regard. In essence, one could say there are different models involved. So let's call it model 1, or Don's model. He's basically arguing the more rooms, the higher the price when you sell it. And in essence, note that it's a causal model that Don is producing here. Why is it a causal model? Because he says, if I do this, that will happen. If I increase the number of bedrooms, I will get more money. That's a causal model, because that's the essence of causality, right? If I change X, Y will follow subsequently in that way. That's causality. If I change X, change in Y will result. That's causality. So we have here, let's call model 1 or Don's model, this simple causal model here. All right. So, well, according to your model that you as a data scientist computed, it looks like a quite good idea. But being a clever data scientist, you've got some suspicion. You've got some suspicion, and you do a stratified analysis. You stratify the analysis that you did previously, bedrooms, the price achieved again. Here are, by the way, each dot is one property that you sell, right? So I try to put the same dots as I did before. In the literature, you can find those plots much more beautiful than I sketch it up here, and I can point out afterwards some literature where to find it. For instance, Pearl, Judea Pearl, to mention that very briefly, is one of the leading figures in and stuff like that. But all right, so here is our properties again, and now you stratify. As I said, you stratify. Say we take small, medium-sized, and large properties. Here are the in green. Let's do it like this. Green, shaded, colored green should be so the small properties. Yellow are the medium-sized properties, and now I sketch it a little bit different in order to make it more simple to see what's going on. Actually, it should be exactly the same dots, but to make it a little bit more vivid. So, and large property. So now we stratified the data, and now let's, you can think about that like having 3 little spreadsheets, for instance, one for the large house and so forth. And now you compute again your regression, so your bivariate trend between the 2 variables, as you did in the first step, but now separately for each sub-data set, so for the large houses. And then look at this. You see, maybe you have, I assume you have had some exposure to statistics previously, and you will see this data, this shape of the data, this pizza form of the data is an indicator of 0 correlation. So a flat regression line, no correlation, no, oh no, Don, hang on, no correlation whatsoever for large houses between the number of bedrooms and the price of the property. Looking at the medium, and of course you already got the point, but for the sake of story, let me finish. Again here, medium-sized houses, no correlation. A flat line, a pizza-shaped cloud of data points, which is always indicating no bivariate correlation. Oh no, Don, what's going on? And same story for the small houses. 0 correlation for the small houses between the 2 variables. Oh no, Don, don't do it. Don't come up with your walls in the room. No walls is your message to Don. Okay, so we have now 2 models. We have here model 1, a bivariate model, and and model 2, a model with 3 variables. Well, again, bedrooms and price, but also a third variable is the size in, say, America, square feet of the property. Okay. Size of the property. Here, for reason of simplicity, just 3 values. Model 2 has 3 variables, and so it's now up to us to ponder how the what model we want to put forward. So we could say, for instance, that both bedrooms, well, firstly, bedrooms again is a cause of the price, and secondly, you could say that the size of the property is also a cause of the price. So this could be a model, and whether it's valid or not. So there are two perspectives on that. So the first is a statistic perspective, and the second is a factual perspective. So there might be a literature, there might be theories that telling us this is a good or a bad model. And many areas of science are at least a little bit developed, or quite a bit developed. So we can say this is a model supported by theories, by literature in our science branch or not. But there's also a third model that comes up to my mind, which is the model of spurious correlation. And here this diagram with the three colors that has a certain feeling to me that we have a confounder model, that a confounder model could take place. And a confounder model is typically this fork type model. Let me show you. So we've got here size of the property as the common cause of both bedrooms and of price that being sold. And if you think about it, it's not implausible. I find it quite plausible because look, size. So that means the larger the house, the more bedrooms you will have as a causal claim. That's a causal claim. So all three models here are causal models. So that's quite a bit of a mouthful. One could say that's a causal model, but like many, if not most, theories in science are causal, right? And stuff people say. Causality is one of the prime interests in life, right? Because only causality allows that my actions will have some result. Think about it. So causality is very essential for life. And here I put forward the larger the property, the more size square feet I have in my property, the more bedrooms I will have on average. Okay, that's a coarse model, of course, a coarse hypothesis, but it's not implausible, I'd say. And secondly, my model 3, M3, puts forward that the larger my property, the higher the price. All things being equal, of course, ceteris paribus, of course, but in essence, larger properties will have, on average, all things being equal, of course, a higher price. So that's a positive connection, causal connection. That's also a good model, or plausible model for at least. So. Yeah, we now have three models, and those three models are quite different. So here in model 2, we had like two causes, two independent variable, if you want. And here we've got one central cause and no causal connection between those two. And yes, we saw an association of bedrooms and price in our first sketch, right? But model 3 holds that's a spurious correlation, a spurious correlation. Spurious correlation means there is an association, a correlation, but it's not causal. That's the definition of spurious correlation. So we end up with three models. And the thing is, just seeing regression, either the coefficients, the numbers, or the diagrams, which at the end of the day is basically the same story, right? So we've got some slope here, in essence, some slope indicating the strength of the association, the slope of this here in the model 1 diagram, so to speak. And here in this diagram depicting causal models M2 or M3, we've got other slopes, and if you just see the two plots, so either this or that one, it's impossible to tell from that which model is right. You just can't say which one is right. More thinking is needed to go beyond it. So, and that's maybe the, so to speak, the sad story of today. Say you'll be reading some paper, you see, okay, here's my coefficient. Somebody is running some analysis and presenting some slope or some correlation, which is a similar measure, saying, all right, the beta, the slope amounts to just some number. And some other person comes up with the idea, oh no, I've got beta x and here two variables, beta x1, x2, and then saying, oh no, the association here is 0 and the other one has some value whatsoever. So two completely different models. So this is what you often see, and I assume you have seen it 1,000 times or 100 times when reading papers, stuff like this. Oh, here's some association, some correlation, some slope of a regression. Could be a difference in a t-test as well. And but it at the same time, here on the right side, it's the same data, 100% same data, same data. The data is completely the same. It could be, here's only one variable considered, here's a second variable considered, and the data points are completely the same. So the data is compatible with both models here, or with even 3 models. You pointed out there might be even more, and you can't just say alone from the data which one is correct. At least if you got observational data. If you got experimental data, stuff is much more clean. Funny things like this, by the way, also called Simpson's paradox in statistics. In experimental data, such creepy stuff will not pop up, but in observational data, you're bound to run in a situation like this. And again, I conclude now, and I'm very well aware that I keep on repeating myself, but sorry for that. If you see this thing or coefficient of some analysis, regression, correlation, you name it, then it could very well be that there are other models with completely different results are compatible with the data by itself. So it's very hard to trust some model without more evidence. And as I said, this is only a problem for observational data. For experimental data, you can't run into this. And well, the solution, of course, is twofold. So firstly, you have to check the statistical properties of different models that might be plausible with the data. So stats check of different models. And secondly, the theoretical base is of course important. Your theories in your branch of science will tell you that either this or that is a good model supported by theories, predicted by theories or not. So both is relevant. And on the one hand side, you might be disappointed or frustrated or even rage if you hear stuff like that. But yeah, I hope you believe me, or maybe I should say don't believe me, read it up. But I hope that you at least find it not completely implausible. So that's the bad thing. Maybe there are different models who can at the same time explain your data similarly well. Different models. Data alone cannot tell the whole truth. And that might come as a surprise. At least it was a surprise to me before I started really working with statistical modeling. So what you need to do is not only know to know how a regression or some other statistical device works, but also you have to really think of your model, what makes sense from a theoretical point of view, and to check the model thoroughly, because, as I said, the same data set can easily be explained by different models. So not only run your regression analysis, also compare different models and check theory, do a thorough theoretical analysis of which models make sense from a theoretical point of view. So modeling is, in that sense, what science is all about.